Thank you. Thanks for the introduction and for the chance to talk to you. So I've been asked to sort of share some kind of perspective from the Generalized Symmetries program. So I interpret this to mean that this is an outreach talk. And we'll see if it is successful by the end. So I'm going to share with you some thoughts on generalized symmetries. And the outreach will mostly be in the direction of the particle physics program. And I would like this to be an informal talk. I assume that it usually is. So please interrupt me at any time with questions. I'm happy to slow down or to kind of derail the discussion if it's interesting. This talk is sort of the reciprocal to Nathaniel's beautiful talk from the particle physics program last week, where he already kind of gave an amazing overview of many, many topics that are of common interest to both communities. And many of us are kind of either historically or presently belong to those two communities, so there really is a lot of common interest, which also kind of extends beyond the boundaries of these subjects. All right, so since you've already gotten such an amazingly broad overview from Nathaniel last week, I thought I'd use the opportunity to maybe try to focus on a few examples and maybe even try to write down a few simple models where I can show you some simple examples of generalized symmetries in action. And I hope that I can do that in a context that will at least give you a flavor for why these tools might be interesting to somebody who is primarily interested in problems in particle physics. And here I'll have a kind of expansive view of particle physics. I mean, of course, it's the job of the particle physics program to tell us what it's all about. But let me take a very expansive view and include everything, the whole standard model at all energies, everything beyond the standard model, everything what you guys come up with. You loosely think of that as particle physics. And of course, this already very expansive blob intersects with sort of even larger and more expansive blobs. One important one, which we'll come to, is gauge theory. Gauge theories, which then has further intersections with all sorts of other subjects that many of us think about, string theory and condensed matter physics, and even those have an intersection sometimes. And other subjects that I'm not mentioning here, information theory, for example. So I'll be mostly floating around in this kind of triple intersection here for most of today. And but if there are any kind of more wide-ranging questions, we can also go there.
So maybe there's a direct intersection between condensed matter physics and standard model.
Yeah,
higher dimension.
That's right. There might be some non-trivial co-cycle conditions and so forth that I'm not capturing here. And the other thing I will restrict myself to, I mean, again, both for reasons of simplicity and for reasons of particle physics kind of applicability, I'm going to talk about theories in 2+1 space-time dimensions. Not because that's the only context in which there's interesting things to do. Quite the contrary. There's lots of interesting work in other dimensions as well. But that's the one restriction I'm going to impose. And even though I'm going to occasionally mention results from the lattice, I will primarily give you examples in continuum quantum field theory. But of course, there's a lot of interest from both sides and both programs in new ideas in lattice techniques as well. All right. So, roughly speaking, the plan for the talk is to give you a very short review of non-generalized symmetries, boring symmetries, very interesting ordinary symmetries. I cannot stress this enough. Ordinary symmetries are amazingly interesting. And maybe something that you might take away by the end of the talk, I hope, is the idea that by attempting to generalize, and in some cases generalizing ordinary symmetries, I think we've actually learned much more sophisticated things to do with those as well, and you know, can now put them to better effect than before. The second part will be a kind of lightning ride through a sort of triptych of generalized symmetries. So these will sort of be the main three examples of generalized symmetries. I'll start with higher form symmetries. And then I'll say something about higher groups and non-invertible symmetries. And to the extent that I can do that, I'll try to stick to one or two very simple models where I can show you how these arise, although there are, of course, many more. And to the extent that I can, I'll also try to point to a few talks that are coming up either later this week or later in the various programs that will relate to these topics. Okay. And if I have time at the end, hopefully I'll say something about gauge theory phases. All right.
Thomas?
Yes.
Since you brought up dimension, is it important for you that dimension is integer?
Integer, very.
You cannot do things like
I certainly cannot. Yeah, it's, you know, when you're doing anything that smells of topology, the notion of dimension is a kind of crucial one. That will be also the case here. So it'll be 3 plus 1 dimensions. Occasionally I'll write things that are in 4D Euclidean, but I would never dare to go away from integer dimensions. Other questions? All right. Okay, so let me start with a very brief flash of things that I want you to keep in mind about ordinary symmetries as we go to the generalizations later on. From the point of view of these higher form or higher group symmetries, these are now sometimes also referred to as zero form symmetries. Different communities have different names. This is the one that's kind of, well, I'm maybe using the string theory convention for what the degree of the symmetry is, which depending on your preferences is off by 1 or not. So these are things that we used to call flavor symmetries or space-time symmetries. And they're the things you teach your students about in quantum field theory class. So, you know, they're all the basic symmetries that you know and love. They come in many subvarieties, which I'm not going to expand on too much. For example, they could be continuous or discrete. Whenever possible in this talk, I will attempt to introduce one of these new symmetries through the lens of a continuous example, because typically those are the simplest ones, and the fact that there's a current often allows me to kind of bypass more complicated arguments. So just for the sake of simplicity, I'll often stick to those. But you should know that there's also a huge and rich set of discrete examples which are similar that I won't get to talk about that much. So what's the simplest example of a continuous flavor symmetry? Maybe like a U1 flavor symmetry with a conserved current, a neutral current, and essentially almost everything that we can say about these symmetries follows from the existence of this current. So, for example, you can integrate the current, and typically what you do is you integrate the current across this time slice. You integrate J0 over a fixed time slice, and then you get a conserved operator. You get an operator whose time derivative or whose commutator with the Hamiltonian is 0. An important generalization, which even though it sounds simple, is sort of at the heart of many of the kind of generalizations of symmetries that we'll get to, is that you should, instead of integrating this operator over a fixed time slice, imagine integrating it over an arbitrary surface or hypersurface in Euclidean spacetime. So you can replace the time slice here by an arbitrary closed 3-manifold and then integrate the perpendicular component of J over that 3-manifold. And that builds some kind of charge that depends on this, that superficially depends on this 3-manifold. But the conservation equation, interpreted in Euclidean signature, plus the Stokes theorem, tell you that, in fact, the dependence on the 3-manifold sigma is very rigid. It's topological. So if you make small deformations of sigma, then you can use the current conservation equation to show that Q will not depend on those small deformations. So this is a topological operator, or topological defect, which measures the charge on sigma 3. And somehow the logical extreme of this small generalization is that one should think of all symmetries as defining suitable topological defects, and conversely, one should think of all topological defects as defining some sort of interesting symmetries. And this is the kind of heart of the generalization that is going to come up in these other examples. Yeah?
Does the codimension one slice have to be Euclidean, or could you have like a...
Sorry, I can't hear you. Can you speak?
Does the codimension one slice have to be Euclidean, or you could do the same thing for like a Lorentzian?
Yeah. For example, that's the example I started with. That's just an ordinary time slice and Lorentzian signature. Yeah.
But a time slice would be, sorry, when you say time slice, are you saying those three coordinates are spatial coordinates?
Spatial coordinates, yeah.
What I meant by Lorentzian, I meant that there's a time coordinate in that codimension slice. So as in one of those would be dt and then d2.
You could. That would, in Lorentzian signature, be have a slightly different interpretation. It would be like a kind of defect instead of a charge operator, but you can absolutely do that, and both are interesting and both are allowed.
Okay.
Yeah. Very good. So let me remind you of a second. So there are many, many things that symmetries are good for, and I'll try to remind you of a few of them because I don't have time to dwell on all of them. Let me remind you one thing that can happen to a symmetry like this. It can be realized in two different ways. Famously, there's the kind of Wigner-Weil realization where the charge Q acting on the vacuum is 0. This charge exists as an operator. It's well defined, and it annihilates the vacuum. In that case, we say the symmetry is unbroken. And as a result of that, the Hilbert space of the theory in this vacuum can be assigned definite charges, or in general definite representations under the symmetry. There's, however, the other famous alternative, which is that, well, one sloppy way of writing it is that Q doesn't annihilate the vacuum. The more precise statement is that Q doesn't exist, and instead, the current acting on the vacuum creates a massless Nambu-Goldstone boson. And then we say that the symmetry is spontaneously broken. So this kind of dichotomy will have generalizations in the other examples as well. And importantly, this dichotomy is sort of at the root of trying to classify phases and phase transitions in the spirit of Landau, right? Let me just finish this sentence. So what Landau taught us is that you should try to characterize phases of matter or phases of statistical systems or phases of field theories by kind of making a list of all the global symmetries and deciding which ones are broken and which ones are unbroken. Yeah?
How do these equations still hold when you have anti-unitary symmetry? And then what does it also mean to spontaneously break an anti-unitary symmetry?
Well, there's nothing wrong with spontaneously breaking an anti-unitary symmetry. You have some kind of pseudo-scalar that gets a vacuum expectation value and then spontaneously breaks an anti-unitary symmetry. What I wrote here is only sensible for continuous symmetry.
Okay.
So time reversal is, of course, first of all, discrete and anti-unitary. But there's absolutely no problem with time reversal. It's a very interesting symmetry. And in fact, I'll come back to it later in the talk.
Okay. And with the annihilation of the state theories, the same equation just be
Sure, absolutely. Yeah. So the anti-unitary time reversal will kill the state.
Okay.
Or not, depending on whether it's broken or not.
Okay.
Okay, very good. Now, on top of deciding whether or not the symmetry is broken and unbroken, there's a kind of whole tower of more sophisticated questions you can ask about symmetries, and I'm going to briefly touch on them, not go into detail. You can ask about things like anomalies, you can ask about things like SPTs, which are sort of a complementary notion in condensed matter physics, and almost all of these in some way or shape or form involve coupling the current operator to some kind of background field. In the case of a ordinary U1 symmetry, that background field would just be a standard abelian gauge field like electromagnetism, but I'm viewing that here as a classical background field. I'm not gauging that. I'm not doing the path integral over it. I'm just using it as a sort of source for my current. And then importantly, the current conservation equation translates into the statement that you can do gauge transformations on big A. That leaves the partition function invariant. And when you study the partition function as a function of A, that's sort of one way to reveal some of this additional, more fine-grained structure, like anomalies or SPTs. I won't do an example here, but we'll get to some examples in a little bit. All right. Maybe one small comment about discrete symmetry, since you already asked about it, is that, of course, in the case of discrete symmetries, we do not have conserved currents. In general, we also do not have these kind of charges. But roughly speaking, what we have are the exponentiated charges, at least for suitable transformation angles. Okay, so some part of this story still goes through for discrete symmetries. All right. So that's essentially everything I wanted to say about ordinary symmetries. And now let me move on to their higher generalizations, starting with higher form symmetries. They're sometimes also called P-form symmetries, where P is some integer. In the case that I just discussed, the ordinary case is the case of a zero-form symmetry. So the simplest non-zero form case is a one-form symmetry, which is going to be the one I'm going to be focusing on mostly. But in general, what is a P-form symmetry? Well, I'm going to tell you what the generalization of this current conservation equation is. There are many interesting generalizations that you might contemplate and that have been contemplated in the literature. You can add all sorts of indices to this current, but then you need to decide how to symmetrize them or anti-symmetrize them. And it turns out that there's a big fork in the road, depending on whether or not you choose to symmetrize them or anti-symmetrize them. Roughly speaking, if you symmetrize them, you'll get some kind of very rigid charges akin to what you might find in an integrable theory. And in general, in higher dimensional field theories, we do not expect such charges to be present unless the theory is free, at least locally free. But if you anti-symmetrize these indices, then you get what's called a P+1 form current. Take a totally anti-symmetric current operator like this, and you insist that it's conserved. All right? And that's the continuous generalization of a zero-form symmetry to higher form degree. And roughly speaking, the fact that these symmetries are anti-symmetrized means that you are kind of evading Coleman-Mandula type triviality constraints, because, as we'll discuss in a second, the objects that are charged under this symmetry are not particles, so they don't participate in the S matrix. As a result of that, the S matrix can be non-trivial even if you have such symmetries in the game. Yeah?
Just because the indicing is already horrible enough, I think it's up to P, right? Because you have mu and then P is.
So it's mu1.
So maybe this should be 2. Thanks. Yes. That's why we'll immediately switch to form notation. All right, thank you. So the moment we have such a conserved current, we can try to play all the same games that we played in the zero form case. Let me restrict to P equals 1. So let me restrict to P equals 1. That's the case that shows up sort of most tangibly in four-dimensional gauge theories. That's why I want to talk about it a little bit. And in that case, this current is a conserved two-form current. And when you integrate it, the thing that you integrated to get a topological operator, the thing that you integrated over also has to be a two-cycle. And so what you get is some kind of topological operator supported on two cycles, which you should correctly think of as some kind of version of a Gaussian flux integral. And indeed, we'll see that the simplest example of this is precisely a Gaussian flux integral in electromagnetism. So let me briefly talk about that example. So the basic, simple, free example is free Maxwell theory, free one-gauge theory. Just a gauge field A and its field strength dA, which is a two-form. And I'm going to assume here that the Bianchi identity holds, so that there are no magnetic monopoles. We can discuss later what happens when you add magnetic monopoles to the system. But F is a closed two-form. You see here, F is the magnetic flux of this Maxwell field, and it supplies you with a closed two-form, which is a simple example of a magnetic flux one-form symmetry. In other words, you can integrate F over closed two cycles, and that measures the magnetic flux through these two cycles. And in Maxwell theory, the Bianchi identity is one half of the Maxwell equations. If you consider the other half of the Maxwell equations, they read something like B star F is the electric current. Well, maybe star of the electric current. And so in general, if you have generic electric currents or generic electric charges in your theory, there would not be this two-form here, which is the sort of electric flux two-form, would not be conserved. But if there's no charge whatsoever, or if the charge is special in some way, then some or all of the electric flux integral can also furnish a one-form symmetry, which would then be an electric type one-form symmetry. So in the context of Maxwell, we will discuss mostly this magnetic symmetry, but later when I move to Yang-Mills theory, we'll also briefly mention the electric example. Sometimes they're also called center symmetries there. All right. So this is a simple example of a very familiar theory with a higher form symmetry. And at this stage, I'm sure that there's nothing new to anyone in this room. The mileage you get from thinking along these lines is that you then get to do all the other things that I briefly reminded you about for zero form symmetries, and many that I didn't remind you about for this higher form case. For example, you can turn on background fields for this symmetry. You can add to the Lagrangian a coupling, which looks something like a two-form gauge field coupled to the dynamical two-form gauge field of Maxwell theory. Here, this two-form background gauge field, which undergoes its own kind of gauge transformations, is the analog of the electromagnetic background gauge field from the previous example, and it captures the fact that this F is conserved. And now you can study the partition function in the presence of this background field. You can talk about anomalies, you can talk about SPT, so you kind of have access to the whole machinery that we know about from the ordinary case. I'll try to mention a few examples later where this machinery kind of buys you something non-trivial. But one thing I want to say here is that, I gave you a reminder of the kind of Goldstone alternative for ordinary symmetries. What you can see immediately is that free Maxwell theory is an example of a theory that has a higher form symmetry that's spontaneously broken. And the reason for that is that the current, the conserved current that I was talking about, for example, the magnetic current, is simply the field strength operator itself. So when you act with that on the vacuum, it creates one photon. It creates a one-photon state. And when a conserved current creates a one-particle state, that means that the corresponding symmetry is spontaneously broken. And that's as true for higher form symmetries as it is for the familiar case. So free Maxwell theory is an example of a theory that has a U1 magnetic one-form symmetry, also an electric one-form symmetry if you don't allow any charges, but it is spontaneously broken. I will later mention examples where of systems that have unbroken one-form symmetry as well. Famously, certain types of confining gauge theories are such examples.
If you don't have electric current, then there are two.
Yes.
And so are there two Boltzmann bosons? Or one?
No, roughly speaking, because there are two polarizations of the photon, and they are enough to account for the Ward identities of the two broken symmetries.
What's the analog of the statement that there is no charge operator?
Pardon me?
So when the symmetry is spontaneously broken for zero-form symmetry, it's that there is no charge operator.
Oh, it's the same.
Yeah.
If you try to integrate the charge operator, the massless Goldstone pole will give you a divergent integral. Yeah, completely analogous.
Can I make sure I understand this again? So basically, the photon phase, U1M and U1E, one from symmetry, they're both spontaneous.
Correct.
So there's a photon, and there are two correlations, but you're saying that these two correlations, they are not two Goldstone bosons.
Well, they are. I mean, you can think of them as two Goldstone bosons, but in a relativistic theory, they come as you can never get one. In a relativistic theory, you would always get both of them.
Yeah, I'm just asking whether these two Goldstone bosons should be viewed as a Goldstone boson from U1E and U1M, or not.
Yeah, for both, roughly speaking.
Sure. The counting implies they should be four, or just two?
Just two. Yes.
So if you have charged matter, then the electric symmetry is not there, but still the photon has two polarization.
Well, then we get into a more sophisticated discussion, which is what kind of matter exactly? Is it massless? Is it massive? The question of whether the symmetry is broken is a question about the deep IR. And so the question is whether the symmetry will remain broken all the way to the deep IR, or maybe it will reemerge below the scale of the charged matter. And those are very different scenarios.
But if you have massless matter,
If you have massless matter, then typically what happens is that also the magnetic symmetry is not spontaneously broken. For example, in massless QED, that's what happens.
so would you say that in massless QED there is no photon?
I would say there's no one particle state that deserves to be called a photon.
Thomas, I think the fact that the Goldstone boson is reduced from 4 to 2 is related to the mixed anomaly.
Yeah, right. Yeah.
You can think about it this way if you want to. That's right. I mean, that's a sophisticated way of saying that the photon has two polarizations, and here I'm using F and star F, so you have access to all of them. But yeah, I agree with you. All right. Let me make one important final comment, and then we'll move on, which is that there's something, even though many things generalize in a straightforward way to these higher form symmetries, there's one very important thing that is different about them, which is that these flux surfaces, which are, let's say, codimension 2 in 4-dimensional Euclidean spacetime, cannot encircle point operators. So if you have a standard local operator, the thing that you study 99% of the time in quantum field theory, at least in elementary quantum field theory, then the only way that a charge can kind of measure the presence of that local operator is by enveloping it in Euclidean spacetime. You can say it in many other ways. You can take the commutator of the charge, for example, with that operator in Lorentzian signature. But the upshot is the same, which is that you need something which is sort of codimension 1 in Euclidean signature in order to detect the charge of a point operator. These flux surfaces are codimension 2. And so they do not detect point operators. The converse of this statement is that point operators are not charged under these kind of symmetries. These symmetries naturally act on extended operators, which are one-dimensional. In this case, they're line operators. They're line defects. For example, this magnetic flux symmetry that I was talking about here acts on line defects that have magnetic charge. Sometimes they're called 't Hooft lines. And the electric symmetry, if it's present, acts on ordinary Wilson lines, which are electrically charged.
So in general, they just act on p-dimensional objects?
In general, they act on p and lower dimensional objects. Yeah. Very good. All right, so this is the simplest possible example of a of a one-form symmetry, of a higher form symmetry. And let me complicate the example just a tiny little bit so that I can introduce you briefly to the other two generalizations on my list, which were higher group symmetries and non-invertible symmetries. And I think in some form or another, people have already talked about them in this program, but we can give a very simple example of both of them by adding to free electromagnetism charged Dirac fermions. So we can consider massless QED we could in principle consider real QED with only one electron, but let me generalize and add some number bigger than one of Dirac electrons. So these are 4-component spinners of electric charge 1, and I'm not adding a mass term. And so let me tell you a little bit about the symmetries of this theory. Okay, this is certainly when n(f) equals to 1. This is probably the one of the most familiar quantum field theories that we study. And the theory has all sorts of symmetries, but let me focus on a few of them. There's some zero-form symmetries, which are essentially, in addition to space-time symmetries, which are there, but let me focus on the flavor symmetries of this model. The massless Dirac fermions have chiral flavor symmetries, just like the quarks in QCD. And so there's an SUN F left and an SUN F right chiral symmetry that acts on the left-handed and right-handed kind of two-component biofermions that live inside these Dirac fermions. And then on top of that, there's a U1 axial symmetry that also acts like the axial symmetry in QED. There are a bunch of discrete symmetries, which I will not talk about. And I've just told you that if you have a U1 gauge theory without magnetic matter, then there is also a one-form symmetry, which is the magnetic flux conservation symmetry, which is associated simply with integrals of the field strength over some 2 cycle. And these are certainly symmetries that the theory has. In fact, all of them have conserved currents. Well, all but one of them have a conserved current. But it turns out that these symmetries sort of mix in non-trivial ways. And this mixing is one of the kind of simplest, most familiar-looking ways in which higher group and non-invertible symmetries arise. Okay? And in this example, they arise through triangle anomalies. So let me say a few things about the triangle anomalies in this theory. There are a whole bunch of different triangle anomalies. We'll discuss 2 of them. And they will both involve some number of photons and some number of global symmetry currents. Let me first consider the symmetry currents associated with the SUN left symmetry. This theory has parity. One second. This theory has parity, so everything I say about the left symmetry will also be true about the right. Yeah?
Is there also a U1 vector?
The U1 vector is gauged. That's the photon.
Okay.
So that's not a global symmetry. But roughly speaking, I mean, you can think of this U1 magnetic as the global symmetry that arises as a consequence of gauging the U1 vector. Yeah. So let me discuss 2 types of triangle diagrams. There's a really famous one, which involves the axial current and 2 photons. And perhaps a slightly less well-known one, which involves the SUN left currents and 1 photon. Both of them are non-zero. Both of them are proportional to NF, roughly speaking, because there are NF electrons running in the loop. And both of them lead to generalized symmetries beyond the ones that I've already listed here. And they come in, they lead to two different types. This one leads to a higher group, and the other one leads to a non-invertible symmetry. Should
This diagram has the photon and then two left currents?
Correct.
Okay, so you're missing an L.
Yep. I'm missing many things, thank you. But that one is important. For example, I'm missing many indices, and I'm going to be very sloppy about those, but yes, I'm considering two left currents. That's very important, yeah. Very good. So, without getting into the details of this diagram and its index structure and so forth, let me tell you roughly speaking what this diagram does. This diagram, roughly speaking, allows two left currents to have a non-trivial OPE fusing into a photon. And a photon, after all, that's sort of the beauty of the abelian gauge theories, a photon is described by F mu nu, which is itself a conserved current for the one-form symmetry of the problem, the magnetic one-form symmetry of the problem. So roughly speaking, you have a kind of OPE-like relation where two left currents, again, indices suppressed, fuse into F mu nu by some kind of singular coefficient, which hopefully I got right by dimensional analysis. This type of fusion rule for currents characterizes a higher group. In general, a higher group characterizes the non-trivial fusion of lower degree or lower form symmetries into higher form symmetries. And in principle, symmetries of all form degrees can mix. This is a simple example where you only have zero form and one form symmetry, so this is called a two-group. But in general, there could be p groups. All right. And one can restate this in all sorts of nice ways using background fields, for example. Can be interpreted as a kind of Green-Schwarz mechanism for this background B field. We won't need that in what I want to tell you about. All we will need is this simple fusion rule. Okay? And the reason I wanted to tell you about this example is not just because it's a simple example of a higher group, but because this fusion rule has interesting implications for model building in particle physics. Yeah?
Sorry, what's the action of C on the current?
Of what?
Of the charge conjugation, because I'm thinking about Clary's theorem. So I understand you didn't write free photons because I guess that vanishes. But then the left diagram, what's the action of the charge conjugation on the current in the left diagram?
Whatever it needs to be so that this isn't zero.
Okay.
Doesn't it just turn it into right-hand currents?
Yeah, the parity does that. I think C doesn't exchange left and right hand, as I thought.
It's okay.
No, maybe you're right. Anyway, I'd have to think about it.
Okay.
But yeah, this is not zero, but by Furry's theorem.
CP is a symmetry.
Sorry?
CP is a symmetry in this area.
C is also a symmetry.
Yeah.
It's just that
I'm just saying C equals P in this case. CP is a symmetry, right?
CP is symmetry does not mean C equals B.
Yeah, exactly.
C is a P.
C, P, and T are all symmetries.
Yeah.
And in P, for example, either P or CP exchanges left and right.
You can't get a triangle term without a gamma 5 by Furry's theorem. But you have gamma 5s in the J left.
That's correct.
Yeah, you do have gamma 5. Switch over and flip sign to become J rights.
I think you're right.
Yeah.
I think you're right.
Question?
Yeah.
How do you interpret the high order terms in the OPE?
I don't know how to assign them a kind of universal meaning. I mean, at the level of local operators, there'll be many higher order terms.
Yeah, no, but this one is...
This one's special.
Yeah, that's what I'm saying.
Because
the other ones don't have any special...
No, they're just some kind of non-conserved operators. You know, they have higher dimension.
Okay.
Yeah.
Can you state this structure in terms of conserved charges? Like, for example, producing some representation theories in previous cases?
So that would be the most dramatic possibility, but that actually doesn't happen. If you realize the representation theory on the ordinary flat space, Hilbert space, without any defects inserted, then this structure actually doesn't modify the charges. It does modify the charges in the presence of suitable defects. For example, a magnetic monopole. Roughly speaking, you can imagine that you insert a magnetic monopole into your theory in the form of an 't Hooft defect. Then this F could integrate to something non-zero, and what you would get is a sort of two-point function of J lefts that have to have a non-trivial OPE. That's some kind of anomaly, some kind of world-sheet anomaly. But no, if you're only doing ordinary representation theory in kind of the standard Hilbert space without any defect insertions, then this doesn't manifest at the level of charges. It does manifest at the level of currents. So that's, in some sense in which it contains higher information.
This is conformal theory? It's not
No.
discrete, is it?
No, it's not conformal.
Okay.
No. As a beta function, yeah.
I'm a mathematician, that's like my, I have to say that before I ask the question. When I think about a two group, there should be some abelian group around and some other group, and some way in which one acts on the other.
Absolutely.
Could you just tell me, like, what are the groups that are?
This is the abelian group.
Okay.
And this is the other group.
Great.
And they have a non-trivial Posnikov extension. That's actually what this anomaly measures, precisely. Okay. So let me mention a little corollary, which when we worked out this example in a paper with Clay Cordova and Ken Intreligator from a while back, we worked out this example, and then we realized that this fusion rule has kind of very general consequences. And I think these consequences are kind of interesting from the point of view of especially kind of bottom-up model building in particle physics. And the reason for that is the following. So in this theory, in QED, I've engineered this example so that the symmetry is exact. So SU2 left is exact, the one-form symmetry is exact, and this fusion rule is just a correct statement. But you could imagine, and you can easily do this, embedding this theory into a more kind of UV-complete, say, non-abelian gauge theory, in which both of these symmetries are emergent. And in most of physics, we're interested in emergent rather than exact symmetries from one point of view or another. And then it's interesting to ask what you learn about the fact that these two symmetries should emerge from the fact that they have this non-trivial fusion. And roughly speaking, what you learn is the following. What you learn is that whenever you have the left side, whenever you have the SUNF left symmetry, you automatically have the right side, because they have to fuse in this way and give you the F mu nu magnetic current. So that means that there's a sort of asymmetry. Right? Having this implies this, but not the other way around. And the kind of mathematical reason for that is that one of these groups, namely the U1 magnetic, is an actual honest-to-God subgroup of the higher group, but the SUNF left is not an honest-to-God subgroup. Yeah.
So that J left is not really considered, right? Because of the first triangle diagram.
No, that's a different current. That's J axial.
J axial is just J left.
No. No. J axial is the total singlet axial current, and then this is the adjoint axial current, roughly speaking. This is the adjoint axial current. The J left is an adjoint representation of SU and F left. I just didn't write the adjoint indices. Very good. So, what does this mean? Well, imagine that you have some kind of theory. It could be a gut. It could be some kind of Georgi-Glasgow model that UV completes QED. And as a function of energy E, you discover at some point that these symmetries are broken. Let's say that you have an energy E left, where the J left is broken. So above that energy. And you have another energy E magnetic, above which the U1 magnetic is broken. So DF is no longer 0. What does this mean? This means you have to somehow put magnetic monopoles in the theory, which is natural in a gut. And then you have these two scales, which are the scales at which these approximate symmetries emerge. And what this fusion rule tells you is that the moment you are below the scale at which the left symmetry emerges, the other symmetry must have already emerged. So there's a kind of universal inequality which says that E magnetic has to be bigger than E left. Sorry, did I get it? Yeah, I hope I got it right.
Can I ask a question?
Yeah.
So maybe this is silly, but since you said that this has no consequence at the level of the filter space, Can I take JL and subtract a half of 15U and call that J prime L and call it dust conserved? And
These guys don't even happen to have the same number of indices.
uh,
J left is an ordinary current with a single index. F mu nu has 2 indices. So, yeah, that will not work. No. All right. Very good. So of course, even though I won't try to present any examples here, there's been a lot of beautiful work trying to think through the consequences of this type of inequality, kind of from the point of view of bottom-up gut model building. Now, of course, whenever you have some kind of gut, it's natural to have magnetic monopoles at the gut scale, and it's also natural for these chiral symmetries of the low energy theory to be somewhat or completely broken, and then this inequality gives you some kind of constraint on these models. And of course, in any weakly coupled model that one studied or that has been studied a lot, that has to be true, so you don't necessarily learn something new in those examples. But it gives you a kind of bottom-up way of looking at how these different symmetry-related scales might emerge, and it might give you a kind of broader perspective on how to organize these models. Yes?
How strict the squiggle is. So my impression is it's not very strict.
It's not that strict. It really says that you can't have a parametrically large violation of this inequality.
Parametric means factor of 10, factor of
No.
100, factor of 1,000.
Anything. Well,
No, for particle physics, we need numbers.
yes. Parametric really means that I can only rule out something that can be made arbitrarily large by dialing something. But I don't know how to rule out.
I'm just saying that is there a way to quantify this better?
Not without further work. I don't know of a universal result like that.
Okay.
So this means confinement implies chiral symmetry breaking.
Sorry? This is QED. There's no confinement, and there's no chiral symmetry breaking.
I'm saying that because if there's a chiral symmetry, the J left is conserved and the F mu is conserved. Right?
Yeah.
But if you can imagine for compact QED, there's still type of confined phase.
This is not compact QED. This is a continuum 4D QED without dynamical monopoles. It has a U1 magnetic. It doesn't confine.
Yeah, but then there's always a confinement.
Yeah.
Okay.
That's the theory.
To make it more useful, you have to think
But that's what I have at long distances. So there could be monopoles at short distances, but at long distances we know that we have magnetic symmetry, right? From the point of view of actual QED.
what actual QED means.
Well, the thing that allows me to see you.
Deconfined phase.
Yeah.
Well, I think to make it more useful, you have to think of the situation where it's monopole and monopole.
Well, so that's the situation I'm thinking about. I'm allowing myself now to think about a possible monopole, but I'm assuming it's very heavy, right? I'm assuming it's some kind of gut monopole or something like that. Of course, if we're discussing something completely different, like a kind of solid state system where there isn't a U1 magnetic symmetry and there isn't a heavy, there isn't a kind of big gap to the monopole.
In that situation, this
Yeah.
implies that the confined phase will have chiral symmetry. Confined phase means that there's no base boson. I mean, there's no photon. If there's no photon, then the JL cannot be conserved at all, even the chiral symmetry must be broken. Has this implication?
You're completely right. So this relationship tells you that the kind of only other sensible breaking pattern is unbroken. So, for example, if you had a confined phase, this would be unbroken. But in fact, that's also the realization of the symmetry in real QED. Roughly speaking, because of the comment from before that this symmetry is actually unbroken when you add massless fermions. Both of these symmetries are unbroken when you add massless fermions in ordinary QED. Okay, so I'm going to run out of time very soon, so I want to switch gears a little bit and tell you about the other diagram and the other type of generalized symmetries that arises when you study it, and that's the ABJ anomaly diagram, which is maybe a little bit more familiar than this one. That's the statement that if you take the singlet axial current without any adjoint SUN indices, then its divergence is something like NF times F wedge F, the abelian instanton density. So this is the famous Adler-Bell-Jaquiev equation. And Unlike in QCD, where this right-hand side is activated by instantons, there's been a lot of humming and hawing over the years about what it means that the abelian instanton density in flat space can't really be activated, can't really be saturated, because there aren't any smooth instanton configurations. And there are various perspectives on this, but one very nice one comes from recasting this anomaly equation in terms of a non-invertible symmetry. And so this sort of ends up giving a structure that is somewhat different from the higher group that I just discussed, although there'll be some kind of similar features as well. And essentially the starting point for this discussion, which was sort of this sort of discussion is due to Ichuo and Otat and Xu Hang, and also Clay and Kentaro Omori in 22. And what they basically explained is how to construct from this non-conserved current operators that are nevertheless gauge invariant and topological, which is the sort of basic thing that you need to ensure, roughly speaking, by improving upon the old but slightly illegal trick of subtracting f wedge f from both sides, getting a slightly non-gauge invariant current, and then fixing that gauge invariance by stacking the defect with the topological sector. So I'm not going to have time to explain any of those details, but thankfully some of the originators are here. And the upshot of this is that you get a defect that is labeled by an angle, which is roughly speaking the angle in U1 axial that you're trying to rotate by. And roughly speaking, you can think of this as the integral of the axial charge, suitably defined so that it is conserved, and then stacked with a kind of TQFT to fix gauge invariance. And this creates for you a dense subset of the allowed U1 axial transformation. It turns out that for kind of interesting reasons, this alpha has to be rational. It cannot be continuous without extra work, which people have also discussed. And the upshot of this is that you get something that sort of tries very hard to be the unitary U1 axial symmetry, but because of this stacking with the TQFT, it ends up being non-invertible. What does non-invertible mean? It means that these U alpha operators are not exactly unitary. And one manifestation of that is, for example, that if you fuse U with its dagger, you don't quite get the identity. Instead, you roughly speaking get some kind of sum over the magnetic flux defect operators in this theory. So you get some kind of sum over the Q magnetic two-form flux operators summed over all possible ways of inserting that. The right-hand side is called a condensation operator, and even though the details are a little bit different, you see that this equation has a structure which is a bit reminiscent of this one, in the sense that you have a fusion of two U1 axial unitaries that's giving rise to something that knows about the magnetic one-form symmetry. And so it turns out that that also has similar implications. That again, there's a kind of...
side non-trivial for flat space? Is trivial?
Well, flat space, so if by flat space you mean flat space without, it's not just about the Euclidean space, it's whether or not you include any monopoles. If you don't insert any monopoles, then the right-hand side is dead trivial. And that's the statement that QED, in the absence of monopoles, has a completely pristine U1 axial symmetry. But, for example, if you insert monopole defects, like a 't Hooft line defects, then this would be non-trivial. Yes. Yeah.
Yeah, here is a field theory story. I wonder whether one can promote this, or maybe promote those to a lattice model. So in the lattice gauge theory, something more regulated, which is, can still show all these features.
Well, but it's I guess the basic worry or the basic problems that in most regularizations, all of these symmetries would be broken. So the question is whether you can...
You're talking about inverter symmetry, right? You're talking about inverter symmetry.
Well, I guess maybe your question is more whether one can make it exact or partially exact on the lattice.
Yeah, but maybe certain usual regulation may break some symmetry, but maybe those symmetry can be emerged in the lattice model. But certainly the best is that even exact in the lattice model, that would be more wonderful.
Right. So, I mean, I'm not an expert on this, but there's a lot of exciting efforts to put chiral symmetries, chiral gauge theories, chiral everything, and anomaly everything on lattices, and I think that's something where the two programs really have a lot of overlap. So there are many experts here that know much more than I do. All right. So roughly speaking, for the reason I mentioned, which is that this fusion algebra resembles this one, there's a similar kind of hierarchy of energies that would constrain the emergence of these symmetries in some kind of model building.
So is the resulting structure you get from these fusion rules, like I have to assign a dimensionality to it, so is it something that would be, like, what dimensionality could you, does that make sense? I don't know how to ask the question.
Well, we know the dimensionalities of the charge defects and of the operators they act on. So I'm embedding this in 4 dimensions. So
if you say non-invertible symmetry, is there some kind of like category thing that's there? Okay, so in like what flavor of category? What's the n of the category?
I think in this case it'll be a 3 fusion.
It's continuous.
Continuous, like and that's looking like some kind of continuous Tombari-Yamagami tree, or?
No, it's a bit worse than
Yeah.
I mean, the right-hand side is like condensation defects.
Okay. And is that a very large type of condensation thing, or is it finite, or is it like a very big type of thing? I don't know if this.
I think these are finite particles. Okay, again.
Well, that's not quite continuous, but then it's not finite either, right? These are irrational.
So I think categorical is not really the type of things that you would look at as a 3 fusion category.
There are variants of this, which are not this, that are more finite dimensional.
There are 3 Tombari.
Yeah.
Right.
So I suspect Ichiro will talk about these tomorrow.
No, we will actually talk about this instead.
Oh, maybe he'll talk about both. Well, I also thought I would talk about many more things, but I'm realizing that I'm almost out of time. So maybe just to sort of wrap up this part of the discussion, and I'll have to kind of postpone any discussion of gauge theory phases to offline conversations. So what in addition to the application to gut model building, there's sort of a number of other interesting particle physics problems where these type of symmetries more or less immediately show up. One is fermion scattering off of a monopole defect, which is kind of related to the famous Kalin-Rubakov effect. And if you would discuss this from the point of view of the low energy QED theory, then you would describe it by this theory in the presence of one or several magnetic defects. And in that problem, the right-hand side of these fusion rules is activated in a kind of non-trivial way, and both of these symmetries are essential in constraining the kinematics of the scattering. So that's something that a lot of people have worked on, and maybe somebody will talk about it. And the last thing I want to mention, especially because Liantel is here, and I think he'll talk later this week, is that the same type of higher group and non-invertible symmetries also show up in axion models in QCD. I won't have time to describe that, but from your title, I'm gathering that you'll talk about it.
Actually, I think Friday talk is cancelled. I think.
Oh, it's canceled.
So I won't speak.
Friday is a holiday.
Are we not allowed to talk physics on Friday?
As long as you don't.
It just won't be recorded, that's all.
No, so it's up to you.
Maybe on the Thursday, I will talk about this action KITP may emerge from this some non-invertible model. Maybe very related to this.
Yeah. So sorry for advertising your virtual talk. But in any case, you're going to ask him exactly. Okay, so maybe I'll stop here. Thank you.
Say you covered P equals 0 and P equals 1. Is P equals 2, is there any unique for it in 3 plus 1? Or
Yeah, axions have P equals 2.
Okay. And
Because they have
I dualize the 3 current into a 1 current?
Well, you can, but if you insist that the current is conserved, then the dual current won't be conserved. So you want a conserved current, and it means that.
I mean, if I have a 3-form current, can I just contract it with the other speeded tensor to make it like 1 form?
Yes, but if the 3 form is conserved, then the 1 form will not be conserved. It will be closed.
Okay.
The currents ought to be conserved. So you can have distinct. I mean, you can still use the language of the dual, but in that case, it will be a closed 1 form. And in fact, an axion is a good example. In fact, any compact boson, because the axion is compact. You can have non-trivial winding around strings, around kind of codimension 2 monodromy strings. And those are protected by winding symmetry, exactly the same type of winding symmetry that you have in 2-dimensional compact bosons. But in 2 dimensions, it's an ordinary symmetry that acts on local operators. And in 4 dimensions, it's a 2-form symmetry that acts on kind of codimension 2 winding defects.
Yes. I think maybe it's already asked. So you mentioned this 2-group structure. I imagine with a pi 1 level 2 group, this is SUN. On the pi 2 level is U1. Is that what you mean by this 2-group structure?
Probably, wait,
Yeah,
which one?
yes.
Or the other way around? Sorry, which way did you say?
The pi 1
Yes.
level is SUN.
Correct. Yes,
and
that's
the
right.
Pi 2 level is U1.
That's correct.
And so that's 2-group.
Mhm.
I mean,
Any more questions? So, so we know that. So I wonder if there's a hierarchy between these 2 group non-invertible and instructive. So we know that when in the presence of the 2 group, the 2th anomaly for the 0-form symmetry is ambiguous.
I don't necessarily agree to that statement. At least you would have to explain more.
Yeah, because like we can. Oh, sorry. Oh, in the presence of mixed anomaly between the 1 form and the 0 form, and then the anomaly for the self anomaly for the 0 form symmetry. Because you can always shift the background.
It's not ambiguous. I think it's not. I think that's that's what I was trying to get at. It's not ambiguous. It's modified.
Okay,
The space of anomaly. That's completely correct. The anomalies of the 0-form symmetry are kind of truncated because you can now cancel certain types of anomalies with counter terms that you couldn't cancel before.
That's right.
Maybe just to elaborate on that just with one formula, one thing that I said but didn't write was that you can rephrase this equation in a non-trivial kind of Green-Schwarz-like transformation rule for the B field. So the B field, which has its 1-form gauge transformation, because of this also acquires a transformation law under the SUN left. So under an SUN left gauge transformation, the B field shifts by something like NF, and then there's a trace and the left gauge parameter and the left field strength. Okay? I think that's what you have in mind. And then you can write counter terms that look something like BM, wedge, something else. Maybe something constructed out of the 0-form symmetry. And then this transformation will look like an anomalous transformation, and that's correct. So what that means is that in the presence of higher group symmetries, local counter terms can eat some of the 0-form symmetry. But that doesn't mean it's ambiguous. It just means you have more counter terms than you thought, and you should reanalyze the space of non-trivial anomalies. And something that you might have thought of as a non-trivial anomaly for the 0-form symmetry might become trivial in the presence of a 2-group. Absolutely. So you can have funny models that I can build, and they're slightly more complicated than the QED models that I told you about, that have tons of triangle anomalies all over the place, a 't anomalies, but they're completely gapped. So if you didn't know about this, you'd be shocked that the 't anomalies don't match.
More questions? Okay, thanks very much.
Thank you.